For the modern world, life, death, and reign in the late Triassic. And Stuart, I believe, has sort of probably talked to you about some aspects of this already, but this is really more of a sort of personal journey as to how I ended up involved in this. I sort of invented it, really. Start off, where were we 234 million years ago, which is late Triassic? We're sort of here, Pangaea, one big sort of supercontinent, one giant ocean, and we're somewhere up there. And it's all a sort of a bit arid. And there were lots of things happening in the Triassic, and the Triassic is actually bracketed by two mass extinctions. And mass extinctions are where loads and loads of things that are not necessarily related all go extinct because of environmental stress or whatever. There's one going on at the moment, and we are the environmental stressor, as it were. So you've got the end Permian extinction, which was the big one, killed pretty much everything. And then you've got the late Triassic extinction 200 million years ago. And I said Earth's 5 or more. I mean, you look, there's these various spikes, and you think, well, how do they decide that is one and that isn't one? But then there was a sixth mass extinction, and that was discovered in 1907, this thing, Carnian pluvial episode, and it was a mass extinction hiding in between two others. And so it was between the end Permian and the end Triassic. And so that's one of the reasons it was sort of not really spotted, because people were really, distracted by those. And we called it the Carnian pluvial episode because it rained a lot. And it's a French word, of course, il pleut, it rains. And it's called the Carnian because the Carnian is a period of time within the late Triassic. The Triassic is subdivided into a series of shorter time periods, of which one is called the Carnian. And this event or episode occurred actually within the Carnian. It wasn't even at the boundary between, say, the Carnian and the Norian. It was within it. So it was another reason why people didn't spot it. And when you look at Google, this was probably a year or so ago, nearly 16,000 results and lots of scholarly articles. You get thousands of results today, but it hasn't always been like that. And of course, when was Google invented? 1998? Something like that. Anyway, so this is all really about, how did we come up with the idea? How did we discover this thing? And it wasn't just me. So this is a living crinoid. They're related to starfish and sea urchins, still alive today, but the stalked ones are mostly deep water. And I had a research fellowship at Liverpool University, 87 to 88, and I was looking at Triassic crinoids, and I was interested in the evolution of them because my PhD had been on lower Jurassic crinoids, and I sort of figured out what was going on there. And the obvious thing is, well, what happened before that? So I was looking at these marvelous Triassic crinoids, some of them very, very sort of beautiful critters. But one of the things that became apparent very early on was that I expected that those amazing Triassic crinoids that are sort of behind there, they disappeared by the end of the Triassic. And I tended to assume, well, they disappeared in the end Triassic extinction. But it became clear very, very early on that no, the big extinction event was here in the Carnian. This big group, which were the dominant group of crinoids, the encrinids, they disappear and the holocrinids disappear. And there seemed to be a lot going on. So, that was a bit of a surprise. Meanwhile, we go to things on land. Now, crinoids live in the sea. They were living out in the Tethys Ocean. So things that are happening on land, you think, well, that's completely irrelevant to what crinoids were doing. This is typical late Triassic sediments that you can see around the Severn Estuary, which is the most fantastic part of the world, to my opinion. Lots of evidence of arid soils and lots of evaporites. This is gypsum now at the Severn Bridge. And here we've got what have I done? Oh no, I just found out what that button does. Ah, that's the one. That's the death ray button. Okay, so this is all the Mersey mudstone. The upper Triassic, the late Triassic is sort of Mersey mudstone. This is all sort of Mersey mudstone here, and it's sort of from the Ladinian stage, the Carnian stage, Norian, and up to the Retian when the sea level rises and floods across the land. So through much of the Mersey mudstone, it's pretty arid. And of course, you've got big salt deposits in places like Droitwich and Cheshire and Northern Ireland as well. But it's interrupted by these sandstones. And before I came here, I actually went to pay homage to the canal cutting at Shrewley, the type section for the Arden sandstone. This is more sort of my part of the world. This is Newnham 7. It's a lovely sort of section there, recently collapsed. And these sandstones interrupt these arid deposits. So quite clearly something's going on. There's enough water flow to actually bring sort of larger particles in. So something has happened to climate. And you see, you go over to Germany, this is the Schilf sandstein, and it might be 35 meters thick there. Great big thick sort of sandstone, sort of channel sandstones. So something quite clearly happened to interrupt these sort of arid conditions. But I wasn't really interested in that. I was interested in the crinoids. I was really not aware of this. But those things that change from arid soils with evaporites to these sandstones indicates that you've got something a bit like this. This is Death Valley, which is very, very arid. And then August 2022, you had sort of catastrophic floods. Anyway, so this is perhaps something that's happening in the Triassic, going from arid, extreme aridity to torrential downpours. And this is where Alistair comes in. Now, Alistair Ruffell, I did my PhD at Birmingham on Lower Jurassic crinoids, and I overlapped with Alistair Ruffell by about a year. So I got to know Alistair quite well. And Alistair was supposed to be doing a PhD on the lower green sand, but he kept getting distracted by some of these Carnian sandstones down in Somerset, the North Curry sandstone. And on one of my visits, 10th of November 1987, in fact, to Birmingham, I went to the office that it used to be my office, but I moved up to Liverpool. Alistair was still there. And he said, well, what are you up to? And I said, oh, well, there's this big extinction in the crinoids, in the Carnian. And Alistair, because he'd been looking at these sandstones and he figured that these indicated climate change, he said, it was raining then, perhaps the crinoids didn't like the rain. And that is a ridiculous thing to say, because he's looking at terrestrial sediments and I'm looking at crinoids that are halfway around the globe in the open ocean. But it got me thinking, oh, perhaps he's got a point. So it got my little sort of brain sort of working. So that comment, that throwaway comment, it was really the sort of start of it all. And what I did then, I sort of thought, well, is it just the crinoids that are suffering this extinction, or are there other things? So I trawled through the literature and I talked to other people. There's a guy who used to be at University of Derby, Andy Johnson, scallop man. He was an expert on scallops, and he had actually documented scallops through the Triassic. And what did he find? Sort of middle of the Carnian, most of the scallop lineages go extinct. So scallops going extinct. There were also sea urchins. Andrew Smith, he looked at those. They were suffering extinction as well. Ammonites always going extinct. On land, there were sort of various plants, ferns, rhynchosaurs. The rhynchosaurs disappeared. Even sort of cynodonts, the mammal ancestors. So there were lots and lots of things in the ocean and on land suffering extinction. So it was a genuine mass extinction. It wasn't just the crinoids. And then we look for more evidence of this climate change. So Alistair's found it on land, sort of in the Arden sandstone, the North Curry sandstone. But what was already known in the Tethys Ocean, and the Dolomites and the Alps, places like that, there was this huge influx of sort of sand and mud in the middle of the Carnian that interrupted a predominantly limestone succession. So you've got these sort of massive early Carnian limestone, spectacular landscape, this in the Dolomites. And then these are Norian limestones. And then you've got this sort of breaker slope here. These are late Carnian sandstones. So basically the rain started there. And what's happening, you've got arid climate, so there's not much mud being brought into the sort of ocean. So you're getting a lot of limestone deposition. And then it rains a lot and it's just washing huge amounts of mud and sand in. And so that's what we see there. It's sort of written quite sort of bold, really. And that could be one of the things that caused the extinction of some of the marine organisms, because all of a sudden there's this mud coming in. And so a lot of filter feeding critters are going to be swamped by that. But it's probably more complex than that. But that's a first possibility, is that it's mud and sand interfering with the ecology of a lot of these marine critters. But one of the key things that really got me thinking that Alistair's point about it was raining then is caves. Now, when I was an undergraduate at Bristol, I used to spend a lot of my spare time fossil collecting. And then I moved to Birmingham to do a PhD on crinoids. And it wasn't so good for fossils, or Jurassic fossils. You see, it was a long way to find any Jurassic fossils. So I thought, well, what did I do? So I took up caving. And when I started, I didn't know anything much about caves, but I very quickly learnt how caves form. And the key bits of, key criteria for cave formation is you need water. You need a soluble rock, which is limestone. And in Britain, it's nearly always carboniferous limestone. And you need a lot of water. If there ain't any water, you're not going to get caves. And so this is actually me back in 1986 when I was slim. And anyway, and basically the more rain, the more and bigger caves you get. And when I was an undergraduate at Bristol, I had been taken to a quarry north of Bristol, a place called Titherington, by one of the postgraduate students there who was working on Triassic caves. These are caves that are formed within carboniferous limestone during the Triassic. And we know they're sort of Triassic because of some of the contents of them. And also look at the sediments. That looks pretty much like Mersey mudstone. And these formed because you had hills of carboniferous limestone exposed in the Triassic. And so if the limestone is exposed back then and it rains a lot, you will get caves forming. And so I thought, the caves are indication of a humid climate episode during the Triassic. And it says their constraints on cave formation suggest they were formed during the Carnian pluvial episode. But it's a bit more complicated than that. And there's been a bit of a disagreement between me and other people for 40 years. Anyway, caves. Caves are really, really important. A lot of people think, well, a cave is just a hole in the ground, but they're not. They're incredibly important things as a place to find things which you thought had been lost. They are like the back of the sofa. So we know in the Triassic there were lots of critters kind of wandering around on the surface, but we do not find their bones and things in the Mersey mudstone. Some of the sandstones we might, but the Mersey mudstone is almost completely barren. Yet within these caves, there's a little jaw of a lizardy thing here called Clevosaurus. That's about sort of a centimeter and a half long. And then these are bones of a small dinosaur called Thecodontosaurus. And so they are like the back of the sofa. Things that were lost elsewhere have survived because it's a very stable environment that these bones end up in. The humidity is constant and they're not exposed to sort of great fluctuations of temperature. But how do we date those cave fossils? We've got dinosaurs, we've got lots of different sorts of lizardy things, even pterosaurs, pterodactyls and things like that. But how do we date them? Well, one of the things is, you look at the Mersey mudstone and I said it's terrestrial. Almost no fossils. We say effectively there are no fossils in the Mersey mudstone, other than the Arden sandstone, which does have some. But then on top, we have what's called the Penarth group, and that's marine. So sea level was rising at the very end of the Triassic, and it flooded across the landscape. And that's got loads of fossils. So people go to places like, this is Horsecliff, and there's a bone bed at the bottom there, which has bones of ichthyosaurs and plesiosaurs. This is a piece of bone bed from West Beyond 7. So there are lots and lots of fossils in the Penarth group, and there are no fossils in the Mersey mudstone group. And yet we've got these things in the caves. So how can we figure out what age they are? I'll come back to that in a bit. My model was that the caves are Carnian. They were formed in the Carnian because it was raining a lot. And the rain falls onto the limestone or falls onto catchments, sandstone catchments, drains into the limestone. And so they formed during the Carnian, and then they were filled in after that, because it's a hole that's there, and so it's gradually going to get filled with sediment. So the age of the sediments might be anything from about 234 million years right up to, say, 200 million. So there's a long, prolonged, once there's a hole there, it can get filled with sort of stuff. And people that agree with me, Pamela Robinson, she was agreeing with me before I was even born. She said they were Carnian, or she said they were, quite old. Well, Mike Sims, that's me. This guy called Nick Fraser, who's done an awful lot of work on the critters. The reason these caves have been studied a lot is because of the critters in them. The lepidosaurs and the dinosaurs and things like that. Most people are not terribly interested in the caves. I am, they're not. But so I'm quite useful to them because I can help them understand how old they are. But most of the Triassic caves, they have these Mersey mudstone-like fills, green and red sediments, and they contain only terrestrial vertebrates. And this is the sort of cave you envisage. This is what's called an epigenic cave. So you've got water, rain sort of accumulates on the impermeable catchment rock and it flows off down little streams. And when it hits the limestone, it sinks underground. And the limestone is soluble and it'll sink down fractures and it'll flow along and down through, down through the limestone to come out at a resurgence or rising or spring down at the bottom. And there are essentially two zones. There's what's called the phreatic or saturated zone. Every kind of bit of the cave below there, below the water table, is completely full of water, so it will dissolve the limestone in all directions. So you get circular passages, tubular passage, phreatic tube. And if there's a lot of mud around, it will tend to fill the lower part of the passage with mud. The mud will accumulate, and the roof just rises up and up and up. And so you end up with a tall passage, which is mostly full of mud. But then above the water table, you get what's called the vadose zone, and that's just like normal surface streams. They're just flowing along the bottom, but they've got a roof on. And so they tend to form slot-like or canyon-type passages. And if the water table drops, you might get a keyhole passage. You go from a tubular passage, it was formed when the water table was higher, water table falls, and the stream then just cuts a notch into the bottom, you see. So that's the basic sort of thing. So what we'll do, we can look at some of these Triassic caves and see what they match up with. But meanwhile, I said they were Carnian because it was raining a lot. This guy called Dave Whiteside, who was a very, very important figure in understanding the caves because he did his PhD on these things in the late 70s, early 80s. And he took me to some of these places. And this is one of these caves. None of this health and safety nonsense. Look, he's wearing a brown corduroy jacket, and he's got a hard hat on, admittedly, but he's got an aluminium ladder there. So what could possibly go wrong? Now, full high biz, all that nonsense. Anyway. But the important thing was that Dave wanted to know what age are these caves. And he's more interested in the critters. So his PhD was really on describing some of the little lizardy things, the sphenodontids. But he wanted to know how old these things are. And he spent a lot of time looking for fossils that he could then compare with fossils from the normal stratified succession. And he found things like this. This is just two of them. He found quite a range of different dinoflagellates and pollen and things like that, and also a few fish teeth. And he could match those with things that were found in the Penarth group, those marine sediments that sit on top of the Mercia mudstone. So he said, right, since I found these fossils here, and we know what age they are because we can compare them with sediments of about 203 million years old, therefore, all of this sediment is that age, Retian. And he said, the caves are Retian, the sediment in them is Retian, everything in them is Retian. So around about 203 million years, and probably only a sort of range of about less than 5 million years. So there's a big gap. I'm saying they're 230 odd million years, and he's saying no, they're about 200. So we're disagreeing by 30 million years. And we've been disagreeing for 35 years. But I think I've got the better of him. And the main group, there's Dave Whiteside, Mike Benton, who you may have heard of. Mike Benton's kind of very famous dinosaur-y sort of person. And basically, there's people at Bristol, the Bristol crowd have been saying for decades, all of the caves are Retian. They're very, very late Triassic. They're nothing to do with the Carnian. Oh, Mike Benton. Oh, about dinosaurs. Oh, right, okay, yes, yeah. So anyway, I'm very good friends with Mike Benton, and I was with Dave Whiteside, but he doesn't seem to talk to me anymore. I don't know why that is. Anyway, but the thing was, Dave Whiteside says these little pollen grains and dinoflagellates and teeth suggest that all the caves are Retian and they're related to rising sea level. And you can actually form caves on limestone islands. As sea level rises, you get fresh water sinks down into the island and it mixes with salt water that's sort of effectively infiltrating underneath. And you get these caves, mixing zone caves, which tend to form, gently sort of dipping zones like that. These are mixing zone caves or flank margin caves found on the flanks of limestone islands. And you can see they're all sort of similar sort of level, and they're not, they're just sort of big, wide chambers. They're not sort of distinct tubular passages. And here's another one, very, very sort of wide. And they're all close to sea level. So that's their hypothesis, that these are flank margin caves and they're not these epigenic things. But when you look at all the Triassic caves, they're completely wrong for this notion that they were formed by mixing of saltwater and freshwater close to sea level. So what we do is we look at passage shape. Remember the little diagram I showed you with the sort of slot-like passages and the tubes? Well, here's one in, this is in the Bowen Island. This is a Vados passage, so it's a sort of tall slot-like thing with a stream at the bottom. And here's a Triassic example. It's quite different from those low, wide chambers that you get in the flank margin caves. And these are what's called paragenetic notches. This is where there's lots and lots of mud coming into the system. And so the sort of mud piles up, it gradually sort of fills the thing up, and the roof just keeps going up, and it causes these notches. And here's similar sort of notches in a Triassic cave. And so this is telling us this is below the water table, a lot of sediment coming in. And also it's telling us that this sediment here is the same age as the cave. The cave is actually forming at the same time it's being filled with mud. So it's not mud that's come along a lot later. So it means that any bones you find in this, and this particular one was full of bones. It was full of little lizardy bones, loads and loads of them. And so they're the same age as the cave. So if we can work out how old the cave is, we can work out how old these bones are, because none of the animals in there match anything we find on the surface. And then this is, again, health and safety nonsense. I used to just rock up to the quarry at Titherington and say, can I have a look round? And say, oh, yeah, fine, off you go. So here I am in my fisherman's smock, no hard hat whatsoever, taking a sort of selfie. This is back in about 1988. And this is a big phreatic tube. You can just see the sort of top of it there. And it's got these little sort of crenulation-y bits here. And there's some Mercia mudstone filling it. And these little bits here are little sort of almost inverted rills you get on the roofs of some caves where they've been almost completely filled with mud, and but they're still below the water table, and water is actually finding its way around the mud, and it's making little sort of mini caves. And so here we've got, a Triassic example. And keyhole passages, this is one in South Wales. You can see it started off below the water table. The water table has fallen because perhaps the valley floor that it was draining to has been cut a bit deeper. And so you get a slot incised into it. And here's another one. There's a little sort of slot there. So they're epigenic caves. They're caves formed by sinking streams. They're not caves that are formed on the margins of limestone islands by the mixing of freshwater and seawater. And what we can do is we can look at almost like the Triassic landscape, because these things were forming in a Triassic landscape of limestone hills and valleys. And then over time, those valleys got filled with Triassic sort of sediments, Triassic mud. And so there's layers, there's a sort of strata within the valley. And we can compare the altitudes of the caves with what we see in the adjacent valleys. And this is actually a bit of Triassic landscape exposed. There's the Carboniferous limestone there. That's good solid Carboniferous limestone. There's a bit of scree, and there's sort of Mercia mudstone with soils and things on there. And this is West Beyond 7, which is a fantastic place. Okay, so this is a pretty much what it looks like at Titherington, sort of idealized section. This is the hills, the limestone hills, going up to about 110 meters, and they go down to less than 50 meters above present sea level. And this is the stratigraphy. You've got the Mercia mudstone group. There's a thing called the Stoke Park rock bed, which is the same as the Arden sandstone. So it's one of these Carnian sandstones formed during the CPE about 233 million years ago. There's the Penarth group with the bone beds. If Dave Whiteside and his cronies were right, the caves would look something like that. You'd expect them to be near to where sea level was when in the very late Triassic, the Penarth group. So that's what you expect to see. That's what you actually expect to see. And this is Dave Whiteside's PhD. So these are sort of passage sections that he kind of drew and recorded, and all the sort of elevations of them. And you can see tall slot-like passages here. So these quite clearly are above the water table, draining down through this massive limestone. So if these are above the water table, it means the valley floor must be somewhere down here. And in fact, you come down to here and we start getting tubular passages. And that's that big one that with me and my fisherman's smock is down here. So it suggests that, in fact, these caves were forming when the valley floor was somewhere round about here, which is the same level as that Stoke Park rock bed, the Arden sandstone, the Carnian sandstone. So these caves are hydrologically graded to a Carnian land surface. And since then, of course, it all got sort of filled up and the caves got filled up with stuff. So this sort of proves really that they are Carnian caves. They're not Retian. And another thing, if the caves really were Retian, then we would expect to find critters in them, some of these Retian teeth. And you see a few, very, very few, but that could be contamination, things washed in at the very tail end. As sea level floods across the landscape, it fills in the last little sort of nooks and crannies within these caves. But we would expect to see some of these things. We would expect to see these in some of these bone beds, and we don't. There's loads and loads and loads of papers that, mostly done by the group in Bristol, have written lots of papers. The Retian vertebrates of Chipping Sudbury, microvertebrates from Westbury Garden Cliff, microvertebrates from Manor Farm near Orst, fossil vertebrate forms of the British Retian. And not a single one of these papers has ever found, they've never found any of these things. And then there's a whole series of papers, again, mostly done by the Bristol group, but some others, Age Fauna and Paleoenvironment of Titherington, Late Triassic Island dwarfs, tetrapods of South Wales, Triassic terrestrial vertebrates from caves on the Mendip, Paleo Island, Late Triassic microvertebrate fauna of Titherington. Lots and lots of work being done on those, and we never find any of these things in those, and we never really find any significant representation of the things from the bone beds in the caves. And the reason for that is because they're 30 million years apart. So these things were long dead by the time these bone beds were being deposited. So, but even then, you see, Dave Whiteside, I like him, he's a very nice chap. But even then he might say, but you need to find a fossil, that you can actually match with things on the surface to say, yes, this is definitely Carnian or whatever. And we can't do that because there is this complete mismatch between what we see in the bone beds and what we see in the caves. But radiometric dating, that's using kind of radioactive isotopes, in this case, uranium lead, of speleothems, stalagmites, stalactites, this is me again. And you can date these things using uranium lead, and you can go back hundreds of millions of years. And for more than 30 years, 35 years or more, I was carrying around bits of flowstone that I'd found in Triassic caves. This is a quarry in South Wales at Ruthin, and this is a little cave here, Triassic cave, full of red stuff like Mercia mudstone, and there was flowstone on the wall. And I thought, oh, marvelous, we could get a date from that. But this is the late 80s, I find that. This is Cromhall Quarry, which is in Gloucestershire, and there's this flowstone layer there. You can see this is Nick Fraser, one of the big names in cave, Triassic cave critters. So we got this flowstone there. And the dating comes out as 234 million, give or take a little bit. In fact, there we go. This is the actual data plotted up. And you see, here's the CPE, and they all straddle that. All the areas all straddle that, and they get nowhere near to the age that Dave Whiteside says they are. So this shows that the caves are definitely Carnian. They were forming during the Carnian. They were being filled during the Carnian, and they were had flowstone deposited there as well. I should say that the technique has improved enormously. The errors on these are really quite small, a couple of %. in 1989, I managed to persuade somebody at NERC, National Environment Research Council. They had a uranium-lead dating setup, and I had persuaded them to date some of this stuff. And the date came back as 240 million years. And I thought, yes, plus or minus 750 million years. And I remember Barbara Barrero saying, I don't think we'll pursue this any further because that's a bit useless. Anyway, but the technique is so good now, and this is Kirsten Drost at Trinity College Dublin, that we get these amazingly good dates. And I didn't tell her anything about these other than saying they're very old. And she came back with these dates, so I was amazed. So it proves that the caves are Carnian. So they're a critical part of the evidence that it was really very, very wet. Okay, so this is a little sort of model of what it was like. This is what was happening, say, 233 million years ago. Very humid climate. This is when the caves form, and there's lots of sediment sort of filling these things in to create these sort of paragenetic sediment-filled passages. So a lot of the sediment is the same age as the caves. It's Carnian. And then over the ensuing kind of 10 million years or so, it goes back to being arid, and the landscape all the time is being slowly lowered, and the caves are sort of being degraded a bit. You're getting collapsed things, and so you're getting a little bit younger sediment sort of introduced. And then we go to 203 million years ago, which is this transgression at the end of the Triassic. The sea sort of rolls across, and it fills in with this sort of gray mud with fish teeth and dinoflagellates. It will fill the last little remaining pockets in the caves. And that's what Dave Whiteside was finding. He was finding the last little bits of contaminants that were filling the spaces, but it wasn't telling you how old the caves are. Anyway, so that's the key lines of evidence for the Carnian pluvial episode, is we've got the terrestrial sandstones interrupting the very arid mudstones, the Arden sandstone, the Shelf sandstone. We've got this huge spread of sand and mud in the marine successions interrupting these thick limestones. And then we've got the caves. And so those really were our three key bits of evidence. And the first announcements we made in December 1988, 30 minutes after the discovery. So we did a talk at a conference, and this was what we call the Simpson-Ruffalogram. It sounds like some horrendous stagnite thing, doesn't it? A Simpson-Ruffalogram. What the important thing was that we had used the evidence for the climate is things like the Shelf sandstone. It's nothing to do with the fossils, so cave infills, karstification, kaolinite, so on and so forth. The fossils we kept quite separate because we didn't want to use fossils as an indication of climate change because it muddies the waters. But then when you look at what's happening with the fossils, we've got extinctions, which are the black spots, and diversification. It wasn't just an extinction event. Things were diversifying. New things were appearing. And these are things in the sea which mostly seem to be sort of things getting quite bad at the beginning of the CP, the Carnian pluvial episode, and things on land, they were diversifying when it started raining, because maybe it's really good. If you're a fern or an amphibian, it's great. And then when it went back to being very arid, the ferns and the amphibians didn't like that at all. So that's when they show their extinction. So the timing is not synchronous between the things in the sea and things on land. And we published 3 papers. This was 1989 was the first one, 1990, and then another one with Andy Johnson, 1994. And they linked climate change with extinctions. You know, there's synchronicity, climate change and extinctions. So I'll come back to that in a bit. And that was about the same time as the first, what's it called, IPCC, Intergovernmental Panel on Climate Change. We're on about, I don't know what number we're on now, but this was the first one. And we thought, this is brilliant, very timely. And this was a letter people used to write to each other in the old days. This was, Alistair wrote to me. I've kept all his letters. I feel a climate bandwagon coming on, so let's not get left behind. And he was true. And I thought, this is it. We are really onto something. People are going to come knocking on our door, tell us about the climate change. And they didn't. Nothing happened. So where were we? Well, one of the first papers, well, actually, if you look at this little thing here, we go along, that is us quoting our 1989 paper. Then you go to 1994. There are two citations in 1994 for our original paper. One of them is our 1994 paper citing ourselves, doesn't really count. And the other one is this, which is titled Rejection of a Carnian Pluvial Event in Europe. And I did always think, yes, we've made it. Somebody is so cross that they've titled their paper Rejection of a Carnian Electrostatic Pluvial Event. Anyway, so nobody really took any notice for years. So, from 1990 to 2006, just 29 citations sort of worldwide. So you thought, oh, where were we? So we just got off, we went and did other things, you see. So I did a lot more caving and was involved in the Caves and Casts GCR with Tony Waltham, the great Tony Waltham, he's not late yet. And also a lot of stuff on lower Jurassic stratigraphy. This was a big volume that I worked on. If this had existed when I was a school kid, it would have been top of my Christmas list. But it didn't, so I had to write it myself. Anyway, and now, meanwhile, Alistair went into forensics, because really geology is forensics. And so he went into forensics because that was really an up-and-coming sort of subject. And he's become, he's a very big name in sort of forensics. He's forever going out, digging up bodies and things like that, looking for people who were dead. Anyway, 15 years in the wilderness. But then, something that happened, we really, neither Alistair nor I were really aware of it. In June 2008, there was a conference, a workshop on Triassic paleoclimatology in a place called Bolzano in Italy. And one of the keynote lecturers, this guy, Paul Wignall. And Paul Wignall, the third man effectively. So Alistair and I, we were talking in his office about the Carnian pluvial episode, that initial where Alistair says perhaps they didn't like the rain. And then I met up with him a few times after that. Paul was in the same office. Paul and I had overlapped for about 2 years. So Paul was listening into all of this stuff. And he says in a book he'd written subsequently, he wished he'd got involved, but he felt he should actually concentrate on his PhD rather than get distracted. Anyway, he was invited to give a keynote talk at this conference on Triassic climate. And he asked the organizers, why didn't you invite Mike or Alistair? And they just said, well, we assume they were dead. They haven't published anything for years. So, but we aren't. Anyway, and things took off after that. So this is, there was an event, that event where you got the limestones, marine limestones interrupted by lots of mud in the Dolomites and things, was actually noticed in 1974 by Schlegel and Schulenberger. And they noticed something, but they didn't really know what was going on, but it was sort of commented on. And then this is us, discovery and first definition of the CPE. Then nothing much happens. And then the Bolzano meeting, and off it goes. And so, so there's 120 published articles by 2020, more than 200 more published since then. So it's really sort of taken off. At the big workshop in 2017 that I went to. And so, actually, that should be the last 5 years. This is recycled from an old talk. So lots and lots of things. There's a Wikipedia page, nothing to do with, actually, I have edited the Wikipedia page slightly, which is very naughty, apparently, if you're directly associated with it. Lots of other things, Mail Online, and they didn't get it completely wrong, because they usually do. And various other blogs and, Lab Manager, I don't know what was a climate, and other people, all over the world doing sort of blogs and things. And then there's YouTube. There's a marvelous thing that time it rained for 2 million years. Now, this is probably a year ago. It had already had 11.5 million views, which I thought, that's not bad. And then we came across, there was music called Carnian Pluvial Episode. This guy's Sconox, Carnian Pluvial Episode, EP. So I contacted him, you see, and he wrote back. He said, hi, Mike, this is really cool. Nice to meet you. I chose that name for the track because I wrote it during our summer here in New Zealand. It was the wettest on record. And I often wondered if it would keep raining for 1 million years. Anyway, so it's gone sort of mainstream. And this is not the only Carnian Pluvial Episode music EP. There's at least 2 more that Alistair's sort of come across. And they're kind of daggers drawn. They don't get on. We like him best. And his music's the most listenable. Some of the other stuff's awful, terrible. Anyway, so it's gone mainstream. But the big questions, there were still some big questions really that need answering. And one of them was that paper that said rejection of a pluvial episode in the Carnian. He was saying what we were seeing was like a Nile in the desert, because you look at the Nile, it's nice and sort of green, but you don't have to go very far before it isn't. So perhaps we're just seeing a rather skewed sample. But in fact, there's lots of evidence all over the place that it was actually worldwide. So this is just two examples. This is the petrified forest in Arizona, which is Carnian. And what we're looking at is clay minerals. You get different sorts of clay minerals appear due to sort of humid weathering versus sort of arid weathering. And so you've got, it's sort of arid there, and then it goes humid, or well, no, going from the bottom, arid, humid, arid. So that's in Arizona, southern USA. And then this was the real, most amazing one of all. These are deep ocean cherts. These are cherts that are being deposited probably several kilometers down, and they're now being sort of on land in Japan. And somebody had the wit to look at these and look at the clay minerals, and it sort of goes up. And then you get here in the sort of Carnian, sort of middle of the Carnian, you start getting clay minerals, which are evidence for humid weathering. And this is wind-blown dust way out in the oceans, in the far-flung parts of the ocean. You're getting this climate signal. So that was the thing that got Alistair really very excited. He wrote another paper called, was a Carnian pluvial episode a review, and that was to remind people that we were still alive, because in case they... And then there's lots and lots of work. There's a whole load of groups now of taking on the mantle and doing all sorts of things. So they're looking at isotopes. So these are carbon isotopes here, delta 13 carbon. And when you get a negative excursion, it means things are getting bad. The environment is stressed. And you see these sort of, there's about 5 of these, CI 2, 3, 4, 5, in the Mercia mudstone on land. And when you look in the marine succession, it's a bit more bitty, but you get 1, 2, 3, 4. So you've got 4 distinct pulses of life's getting bad for everything. And then oxygen isotopes, they can tell what the temperature is. They can also tell you, give you an indication of freshwater influx into the oceans. And this is, look, you've got +2, +6, and you've got, the temperature's going up, going down, going up. And then mercury. Mercury is one of the interesting ones because mercury is quite a newish sort of thing. It's an indicator of volcanic activity, sort of massive volcanism. And you've got these spikes, mercury spikes. And so that's suggesting you're getting 4 big pulses of volcanism somewhere. And remember, we got 4 or 5 of these spikes in the carbon isotopes. And then there's a big discovery in 2013, and it wasn't a really discovery. People knew these were here. This is the Rangelia flood basalt province, which is huge and also mostly inaccessible. There's bits on Vancouver Island, Alaska, and such like. This takes days to hike in here. More than 3 kilometers thick, about 1 million cubic kilometers of basalt lavas erupted. And these were confidently dated for the first time, and they come back as mid-Carnian. So there we have the smoking gun, because we suggested in our original paper, we said, we think it's volcanism, but there was hardly any volcanic rock of the right age. And then this is discovered, and so suddenly that explains those mercury spikes, and it explains an awful lot what's going on. The CPE was caused by probably huge outpourings of CO2 from this volcanism, and then global temperature goes up. The whole hydrological cycle is speeded up, and so you're getting more and more rain. You're getting probably a 10-fold increase in rainfall, sort of 5, 6, 7 degrees centigrade rise in temperature. Yeah, so there you go. CO2 levels probably went up to 1,200 parts per million against 424 now since I did this. And global temperatures rose by more than 6 degrees centigrade. And the effect of that is it just rains a lot more. We see it today. It's raining a lot more. Not today, but recently. Look at Florida. Okay, so it's not just another mass extinction. It was also the dawn of the dinosaurs. And of course, the press, Mail Online again, of course, they cottoned onto this because dinosaurs, everybody loves dinosaurs, don't they? I don't, I think they're really boring. But everybody loves dinosaurs, and this is where dinosaurs really got going. Before the CPE, it's 100% Crurotarsans, whatever they are. And then in the CPE, it's 50% dinosaurs, and then it's nearly all dinosaurs after that. So the dinosaurs really got going. So the media loved that. But it was also the dawn of the dinoflagellates. Dinoflagellates are little sort of marine algae, and they were invented. They first appear in their sort of modern forms during the CPE. And then they kind of really diversify, from the Jurassic onwards. But now this, you recognize him? The Cat in the Hat, Dr. Zeus. And these there, to remind me, there's this one group called the Zeusiaceae. Zeusiaceae. They're not named after Dr. Zeus. They're named after another Dr. Zeus, who was an Austrian geologist. Anyway, and you see they appear round about the CPE time, and they trundle along, and then they just sort of disappear. And you think, oh, that's a shame. But what we need to realize is that reef corals, Great Barrier Reef and all that, the reason these reef corals are so successful today is because they have within them, they have what's called zooxanthellate algae, which are dinoflagellates. And the form of the dinoflagellates that you find in reef corals are very similar to the Zeusiaceae from the Triassic, you see. So probably the Zeusiaceae didn't become extinct. They're just hiding in the corals. And you look what happens, CPE, corals became extinct at the end of the Permian, and then they sort of effectively reinvented themselves, different group. And they really didn't do very much until the CPE came along, and then bang, they just diversify hugely. And that's because of the dinoflagellates. Remember I was saying that one possible cause of the crinoids going extinct might be, there's a lot of mud and sand. I think much more likely is what's happening. You're getting fundamental changes in the marine plankton. So you're getting dinoflagellates appearing in huge numbers. And also the crucible of the coccoliths. Coccoliths, of course, are the tiny, tiny marine algae that are what chalk is made of. And the first coccoliths appear in the Carnian. And then you can see they kind of diversify, and they sort of doing quite well today. And the first true mammals, maybe, the first of our distant ancestors. This was just something I came across. Mammal ancestors shrinking in ears may reveal when warm bloodedness arose. And then they say, sharp rise in body temperature, 233 million years ago. That'll do nicely. Yes, so Carnian again. Mammals owe their success. So if we hadn't had the Carnian pluvial episode, which effectively marks the dawn of the modern world, there'd be no dinosaurs, and that's no birds. No coccoliths, so there'd be no chalk. This is chalk in Northern Ireland. No dinoflagellates, no coral reefs, and no mammals, no us. I mean, things, of course, would have panned out a bit differently, but the world would be very, very different from what it is today. And so the question is, did we miss the bus? No, I don't think we did. We actually inadvertently, stepped off the bus. The bus was moving, but we didn't realize, and we stepped off, and then it kind of went off without us, and we've been trying to catch up ever since. But there's some interesting things, climate catastrophe paved the way for the dinosaurs' reign. Some workers have proposed that this wet intermezzo, the CPE, useful analog predicting the effects of future greenhouse on land ecosystems and ocean chemistry. And it is. It's a very, very good ancient analog for what's happening today. So we were right all along. We are Lazarus taxa, living fossils come back from the dead, not dead. And that's Alistair in a wetsuit. But it doesn't end there. This is a marvelous cartoon I came across in The Guardian a few years ago, you see. It's this notion that somebody has the idea first, but they don't get the credit. And the person who has the idea second, they don't get the credit either. And the person who had the idea third, they don't get the credit. And then at one point, somebody will come up with the same idea that several other people, and they say, oh, wow, that's fantastic, it's marvelous. And this happened to us. So September 2020, this was all over the press, discovery of a new mass extinction, new mass extinction, and it triggered the rise of dinosaurs, blah, 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 and I thought, what? What didn't they read in that title? Synchronicity of climate change and extinctions in the late Triassic. So they conveniently seem to have overlooked that. And we did get a little bit of credit in some of it. Alistair and I got a bit of credit for actually discovering the CPE. But one of the articles, it made me very cross. She actually said, Sims and Ruffle discovered the climate change, but they did not discover the extinctions. And I think, no, they did. But anyway, there you go. But it's become very mainstream. So we've got musical EPs, and we've got YouTube and things like that. And I guess you've probably all seen the Chris Packham program, the Earth documentary, Very, very good. And notice he's wearing the same sort of jacket as Alistair was in one of those very early pictures. Early on, yes. Anyway, there is Alistair, and you can see in the background, that's the Carnian pluvial episode. And so the first episode of his Earth program, for most of it, he talked about the end Permian extinction. And then for the last 10 minutes, he was talking about the Carnian pluvial episode. But he didn't mention it by name, which was a bit annoying, you see. So we feel, yes, well, you've at least... And we get a mention in the book, apparently. I haven't bought the book, but I'm told we get mentioned in it, which is nice. And I like Chris Peckham anyway. I had dinner with him a few years ago. And then if you happen to be in Japan, there's a documentary that came out in April this year. This was filming back in January. I had this, Alistair and I, we both had this email from this Japanese, well, it's actually, she's Italian, but she works for this sort of Japanese company. She's very fluent in Japanese. And she said, oh, we are making a documentary about the Carnian pluvial episode. We would like you to be involved. And we thought, yeah, scam. But anyway, so I replied, and it was true. And they turned up, and they paid for my travel over there, and they put me up in a nice hotel and paid for all the food and such like. So here we are at talking about arid mudstones and evaporites and things at Orse Cliff, and there we are. There's the Arden Sandstone at Newnham 7, and here we are. That's all the sort of interrogation, asking questions about the CPE. But unfortunately, it was only in Japan, and it was in Japanese. But fortunately, the bits that I did were in English, and Mike Benton was in it as well, and his bits were in English. So, and you can sort of get the gist of what's going on. But I thought it's nice that it's got its own program all along. So anyway, I'm going to leave you there. This is in gestation. This is what's that? It's probably about 8 months after we'd come up with the idea. And this is me, the short one. Actually, I'm down the slope. Look, I know I'm short. And this is Alistair, who is, of course, quite tall. And this was Tony Hallam, the late, great Professor Tony Hallam. And he was our PhD supervisor, both Alistair and myself. And this is at Westby on 7. It's quite funny because Tony, he didn't like the idea at all when we first came up with ridiculous idea. But he did come round to agreeing with us in the end. He did think that we were perhaps right. Okay, happy to answer any questions. Thank you.